there's a question. Okay, so we want to consider the case that somewhere we want to take the expansion about c sub 0, but there's a singularity as before, but then there could be a singularity somewhere around c sub 0, or c sub 0 is a singularity, which is more commonly we'll consider that case, but we can generalize that somewhere there would be another singularity somewhere, or more than one singularity. Doesn't matter. Then how can we do the treatment? Just following the treatment. Obviously, we cannot just consider this circle, because then we cannot use the Cauchy integral formula, because you F is the singularity inside. So in order to do the go through this treatment, you want to kind of isolate all the singularity with another circle. So you choose another circle. This is now called this C sub 1. I think it's C sub 1 in your textbook. There's another big, yeah. The outer one is called C sub 1. You consider another circle that enclose all the singularity in the inner region, which may be just one point C sub 0, which is most likely the case. But then we later consider if C sub 0 is a singularity itself, then the second circle will be any circle that has a finite radius. But we generalize that to just maybe there's more than one singularity. They choose another circle with radius that is larger than the distance from C sub 1 to any singularity inside. So this is called C sub 2. And now, after you encircle all the singularity, then within the region, this is annular region, between these two circles, and F is analytic. Now we want to form a closed loop that then this argument can go through. So we can now do something that we did before, just do a detour from C sub 1 to C sub 2, just draw a straight line from C sub 2 to C sub 1 to C sub 2, and then going the negative direction of C sub 2, going around. Now this is clockwise rather than counterclockwise, going around this loop, clockwise direction, and go to nearly the same point, and then go back from another straight path. So there's a path going in and path going out, and this two path is infinitesimally close. Okay, and F is assumed to be analytic, and also that means that it's continuous also. So later on, this integration from along these two paths will cancel because they are in opposite direction. And then you go along C sub 2 again, C sub 1 again. So C sub 1 going in, negative C sub 2 going out, going back to C sub 1. Okay, now this is a closed curve, right? This is like a deformed closed curve. So any point within this region, Fz is analytic. Okay, then we can go through the whole thing, but I want to keep this a little bit. Let's get some space here. Okay, I want to follow basically the same thing. We go a little bit beyond here. So Fz still, you can still use the Cauchy integral formula, 1/2 pi I, right? But there's now the two paths, right? There's C sub 1 and C sub 2, right? And so one is along the C sub 1, the circle C sub 1, and then it's in the forward direction, or the counterclockwise. C pi minus C, right? But there's two paths that go in and out, but they cancel, so we can just say that they add up to the zero. So we just consider the other path. The other path is going clockwise, so there's a negative sign along C sub 2 and the same increment. Okay. Yeah. Which one? The loop, this one? This is C sub 2. This is a loop C sub 2. C sub 2 is defined, always defined as counterclockwise. Yeah, this is counterclockwise going this way, like the C sub 1, but the loop, the deformed loop is requiring to go clockwise, so therefore you have a negative sign. We go. There's a Z. So Z is any point within this region that is now is analytic. This is Z sub 1. That is, we already assume that there's a singularity outside a certain point, that you have the first singularity that away from C sub 0. That's still there. And so the treatment, whatever series will not, the radius of convergence cannot go beyond this one. The radius convergence basically is C sub 0 to C sub 1, not including the circle. So the series, whether the series converging with the exact C sub C minus C sub 0 equals to C sub 1 minus C sub 0, the radius of the distance, that is undetermined. Yeah.
So by principle, the Z sub 0 should always be the singular point, because I see some places they say that Z.
Yeah, that's the usual consider, but this treatment is valid even if C sub 0 is not a singularity, just you have a bunch of singularity inside, that would be fine also. This treatment will go through. It doesn't have, this C sub 0 doesn't have to be a singularity. It's just within the region that we consider, but it can be a singularity also. And that's the usual case that will actually apply this thing. But this writing is somewhat more general situation. So again, and it doesn't matter because we are consider taking the series expansion over the annular region. We are not going beyond this one. So we will never actually evaluate the series exactly as C sub 0. We'll see that it will blow up. The series is called Laurent expansion. Is generally there's a singularity series, but we are not evaluate that near the C sub 0. Is that okay? So C sub 0 can be regular or singular. Okay. And we'll see that in a moment. But we're going through exactly the same process like what we did last time. So now this one, you can write like do the same thing. So like C prime minus C sub 0 and minus. You can actually take this. Let's one more step. Because the two terms, the treatment is slightly different. This is C sub 1 minus C sub 2. Well, we can do the same thing, but on C sub 2, the C prime on C sub 2, right? The distance from all the C prime on C sub 2 to the center, which is C sub 0, is less than the distance from Z to C sub 0. So the expansion that we use actually take out Z minus C sub 0. So we add C sub 0 and subtract by C sub 0. So first you can do is move the negative sign inside. This becomes C. So this becomes plus. This becomes C minus C prime. But you minus C sub 0 and then minus C sub 0. Okay. You see what I did? So put the negative sign inside, reverse the order of C and C prime, and then subtract C sub 0 plus C sub 0. Okay, and now we can do exactly like this now. Now, see, so sum of the n, do expansion, C sub 1, that's one, because we, now this one we take out this C minus C prime minus C sub 0 factor and divided this to the C minus C sub 0, so that becomes C minus C sub 0 divided by C prime minus C sub 0 to the n power. That's the first term. And the second term is same thing, but now we are taking Z minus C sub 0. And then this divided in the denominator. This is C prime. And C minus, reverse the order, C minus C sub 0 minus C prime minus C sub 0. Okay, C prime minus C sub 0. C minus C sub 0. The n power. C prime. Okay. And now do the same thing, just taking all the factor that is not dependent on C prime out. So this is Z minus C sub 0 to the n power, that out of the integration. So here, this is in the new denominator, C minus C sub 0 to the n power in the denominator, which is C minus C 0 to the minus n power, right? But, we can write one more step before the general formula. That the first step would be like this one. So you have integration. C sub 1, F C prime, F D C prime, divided by C prime minus C sub 0 to the n power, n plus 1 power, because there's one more. And that is multiplied by C minus C sub 0 to the n power. This is exactly this one. This is exactly this one. And this one is the second term is now it's integrating along C sub 2 at C prime, C prime, and well, I should, that's integrand that actually doesn't have to do with it. Actually, because the integrand is C prime minus C sub 0. C prime minus C sub 0 to the n power C prime, that's the integrand, and divided by n plus 1 power. Okay. Okay, so that now that you can already see that this the first part is like the theta expansion, except that one more subtlety. You cannot go from this to the n derivative. This is not true. So this is not the n derivative divided by n factorial. Going from this to this one requires the Cauchy integral formula, which require f analytic, but f is not analytic within here, so you cannot do the Cauchy integral formula at, especially at evaluate the derivative at C sub 0, which can actually be a singular point. C sub 0 can be a singularity, so the n derivative might not exist anyway. So you need to keep the integral formula. The coefficient is not equals to this derivative. And now you have a second series. Again, you have the integral, but the integrating of in positive power of C prime minus C sub 0. This is a negative power. So n start from 0, right? 0, so 0, which is 1, and then N is 1, this is 2 in the denominator. This is starting 0, 1, 2, this is in the positive power. Right, divided by c minus c sub 0 in negative power. So this is not including in the usual Taylor series. So including everything here, this is called the Laurent series, that including some possible negative power of your expansion factor. Okay, and the final step is you recognize that you can like combine the two terms and then call it a single series, because this is, let's just consider the integral. This is start from 0, right? 0. This is just a constant 0, 1, 2, 3, and this is start from 0 is -1. The whole thing, including this is in the factor is in denominator, means it's c minus c0 in the -1 power and the -2, -3. So that from all the negative integer to 0 to positive integer, so both term can combine to a single term, except now you're summing over n from all the integer minus infinity. And then any curve within c sub 1 to c sub 2. The c sub 1 is outer curve, and c sub 2 is inner curve, but they are within the region that the f is angled. So any curve within it, because c would be fine. We'll give it the same value, because we already argued that as long as this path is not causing any singularity, you can deform it. So you can deform this circle to c sub 1 or deform this circle to c sub 2, because it's not passing any singularity. Okay, so you can call it C, and then you can just keep the formula, just use this the notation of the first term. Minus C sub 2. Combine it to a single form, single expression, and then just keep in mind that now there's a possibility that n can go to negative. So that the negative n part will include the second term, the new terms in the Lorentz series. Okay, so that would be a final result. Okay, this is F. C. For Z within this annular region, you can do that, this expansion. And then the coefficient is given by this integral. Okay. And I mean, you can call that now, call this A sub n. So now equals to sum of n, A sub n is eliminated C sub power n. Okay. So the A sub n will be given by this integral. Did I miss all the 2 pi r? Yeah, I missed all the 2 pi. Yeah. Also 1/2 pi r. And then A sub n will be 1/2 pi I times this integral. Okay. All right. So that is the Lorentz series.